Hello everyone, this is Sheikh Hania of Sri Venkateswara College of Engineering pursuing my sixth semester. So today we will be covering the topic from the subject Computer Graphics and Fundamentals of Image Processing. So proceeding forward, the contents we are going to cover here is Introduction to CGIP, Transformations between two-dimensional coordinate system, which is our main topic, some explanation and followed with examples and summary. So now we will be discussing about transformations between two-dimensional coordinate systems. You can see what two-dimensional coordinate system looks like. So computer graphic application involves coordinate transformation from one reference frame to another during various stages of scene processing. The viewing, routing, transform object description from world coordinates to device coordinates. From modeling a design application, individual objects are typically defined in their own local Cartesian reference. These local coordinate description must then be transformed into positions and oriented within the overall scene coordinate system. A facility management program for office layout, for instance, has individual coordinate descriptions for chairs and tables and other furnitures that can be placed into the floor with multiple copies of the chair and other items in different positions. Moving forward, also scenes are sometimes described in non-Cartesian reference frames that take advantage of object symmetrics. Coordinate description in the system must be converted to the world coordinate for processing. Some examples are polar coordinates, spiral coordinates, ecliptic coordinates, parabolic coordinates. Moving forward with the topic, as you can see in the figure, the Cartesian XY system specifies the coordinate origin x0 and xy0 and orientation angle theta in the Cartesian XY reference frame. You can just refer to the figure. And moving forward, the transform object description from xy coordinate to xy coordinates, we set up transformation that superimposes the xy axis into xy axis. This is done in two steps. That is, translate so the origin x0 and y0 of xy system is moved to the origin 0 0 coordinate of the plane, and then rotate the axis into the x axis. So you can just see the figure how it basically happens. The translation of the coordinate origin is accomplished with a matrix transformation, that is T is transformation basically. So we have minus x naught and y naught, and these are the matrix shown. And the orientation of two systems after the transition operation and then appear in the figure. To get the axis of two system into coordinate, we then perform the clockwise rotation. So moving forward, the translation taking place, we can just see the figure. The positioning refers to the frame shown in figure 30 after translation, the origin of X system. So we can see in the figure the how it is happening after we rotate into clockwise direction, and this clockwise rotation matrix is obtained. So concatenating these two transformation matrix gives us the complete composition matrix for transforming object description from XY plane system to XY system. So comprising of T and R, we have the following formula. Moving forward, an alternative method for describing the orientation of XY coordinate system is to specify a vector v that indicates the direction for the position y-axis. As shown in the figure, we can specify coordinate v as a point into xy reference frame related to the origin of xy system, which can be converted into unit vector. So another system to know the coordinates is the vector formula, which is given as v is equal to capital V by modulus of v, that is Vx and Vy. So we can obtain unit vector u along the x-axis by appearing 90-degree clockwise, rotating to vector v. This is the next formula we'll be getting when we rotate the 90-degree. Finally, we can see that we noted that the elements of any rotation matrix could be expressed as elements of set of ortho orthonormal vectors. Therefore, the matrix to rotate xy system into coincidence that with xy system can be written. So this is the following matrix we'll be getting after rotation matrix. Next, for example, suppose we choose orientation for y-axis that v is equal to -1, 0, then x-axis is in the position y and the rotation transformation matrix is. So for example, if we rotate to the axis y, we can see the matrix. And these are two figures showing the following matrix how the transformation is taking place. So equivalently, we can obtain the transformation matrix from equation by setting the orientation as theta 90 and interaction application, and may be convenient to choose a direction of v relative to position p naught. So basically we can just rotate it as we want to the y-axis, and we obtain unit vector u and v would be then oriented as shown in the figure, and we have the following formula, and then u is obtained as a perpendicular to the v that forms a right-handed Cartesian system. So in this system we can see how the transformation in 2D objects takes place. By the following figures and matrix formulas we can finally conclude that how transformation of rotation and then due to addition of matrices how the final answers solution maybe takes place. So thank you so much. I hope you understood. Thank you.